So we got 2 lectures, as I said, and the first one is about computer hardware. Architecture in this case is talking about like you would design a house or something like that. So how would you design a computer, and then what would be there when you did? So that's what we mean by the computer architecture. What are the components of the computer and how do they work together? Then there's a little bit here about artificial intelligence. So when we say artificial intelligence, what we mean is, can a machine means computer, can a machine be like a person? There is a fairly big field in that. You can do a degree here at this university in artificial intelligence and in many other universities. Artificial intelligence is used to power all kinds of devices that we have. So for example, the Google assistants that you have and Siri that can talk to you and talk back. I mean, there's some artificial intelligence that's required to sort of recognize people's natural speech and respond to it. It's not perfect, as you know, right? So they've done a lot of work to sort of make that happen. Self-driving cars, that would definitely be in the realm of artificial intelligence, where you got a machine that can sort of pick up all kinds of sensory information from around it, and from that navigate and drive safely. Even below the level of self-driving cars, there's many cars on the road today that give all kinds of warnings to people. There's cars that can park themselves, right? You know, you get in the car and you press a button and, you know, park, and it'll do the parking thing for you. There's cars that if you are driving down the road and you go outside your lane, you get a warning. And there's cars that if you're driving and you've got, you're in cruise control and you're driving down the road, they have adaptive cruise control. So if you get too close to another car, it'll slow down, even though you're in cruise control. So there's a lot of sort of, and I guess you could say even maybe your ABS braking is a sort of a basic level of sort of artificial intelligence, where you've got some kind of decisions based on input, which changes quite a lot. So computers do that. Now, in every one of those cases that I just mentioned, that we sort of talk about that being maybe artificial intelligence, in every one of those cases, it's a fairly limited realm, right? It's not a general purpose intelligence like a person. So what I mean by the general purpose intelligence like a person, you put a person in a car and you tell them to drive the car, and they do that, and they do okay with that. They're able to take in all kinds of sensory stuff. They get out of the car, they go and sit down at a spreadsheet, and they do some stuff there, right? And then they go and play a game of tennis. All of those things are very different from each other, and they all take intelligence, and humans can do all of those. But you know, I don't know a computer that could do all of those things. You know what I mean? So you know, maybe they can do one of those things. That to have general intelligence like a human has, I don't think we've got there yet. When we do, well, that'll be scary, I suppose. So yeah, but what they are really, really good at is computers can do things really, really fast. And so, for example, the first implementations of computing was big companies. Well, I mean, you saw the IBM company was drafted in to help with the American census. And census is, you know, 100 million people back in those days. Nowadays, it's like 330 million people. But, you know, it's a lot of people, and you got to sort of go to, you know, that's a lot of records. It would take, and it did back in the 1880 census, it took them like 10 years to sort of calculate the results so that they could do the analysis. And computers sort of nowadays, you know, you have a census and the results are out in a couple of weeks. So that's a big thing. And yeah, so they can do calculations really, really fast. Same calculations. Banks use them, you know, to send out your bills and stuff like that. They're, as it says there, they're reliable and precise. I guess you could say, yeah, precise. There's another word similar to that, which is accurate. Yeah, but precise is good, meaning that, you know, with your mathematical calculations, you can get them to many, many decimal places. That's really useful if you're going to be doing like space travel or something like that. You know, you need to plot your trajectories of your rockets to be very, very accurate and precise. Otherwise, you miss the planet that you're heading for or whatever. Well, the moon. And they don't get tired, yes, like people do. And so, yeah, they don't need holidays and they don't need days, time off at the end of the day. They don't need to work for 8 hours. They can work 24 hours a day, etc. Can we program them to do anything? Well, yeah, I mean, that's why you guys are here, I suppose. There's been a huge sort of industry in computer programming for the last 50 years, and it doesn't look like it's letting up. I mean, you know, if you can write code, you can have a job writing code. There's lots more opportunities for writing code to be out there. And as we see, writing code for what? I mean, you know, you might be writing code, as I said, that's going to go into a car. You know, that makes this car do this or that. As I said, you know, lane departure, all this kind of thing. Yeah, you can meet a specific need. Now, I'm just looking at there what it's saying there. Power supply, what's that? Programming is really cool. Yeah, it is. Yes, problems are not. There are some problems that are not computable. There's this thing called a halting problem, which was. I'm sorry, I didn't read up on this morning. That one I missed, but it's probably worth us looking at later. The halting problem. Turing proved that there was this problem that couldn't be solved by a computer. I don't know if that would be revisited. Yeah, maybe now it is. This is just a little, okay, what you're looking at now is this cartoon that was very famous, and everybody in IT used to read these cartoons back in the 1980s. And yeah, and it was always making fun of managers and particularly IT managers, but yeah, managers who would ask programmers to do stuff which was really dumb. And you know, this is an example of that. So, you know, I can do this program, you just tell me what you need, what you want. Well, I was hoping that you would do the program, and then I'd know what I'd want. I want you to write the program so that we know what it is. So it's not too far from the truth. The thing that makes cartoons funny is if it's a little bit like the truth. And so it's not untrue for people to want you as the computer programmer to come up with the ideas of what the program should do. And of course that can cause problems because we have a scope creep sort of concept, which is where the program initially was going to do, you know, X, Y, and Z. But as we looked at it, we realized we could do A, B, C, D, X, Y, and Z. And eventually we end up with A, B, C, D, you know, and then we have cost overrun, lots of problems like that. Is it possible that the computer is limited? Well, yeah, the world is limited. We live in a finite world with finite resources. Finite computers, definitely they have finite memory, and they have finite speeds. Finite, you know what I mean by that, right? That it doesn't go forever. It's got some limits. And so there is some capacity limits on there. Okay, so these terms hopefully are familiar to you. If we say hardware, that's really something that you can touch. It's not, so all of this stuff here is hardware. And it's, you know, we would define that looking at our computers as the boxes and all the things that plug into the boxes, and all of that's our hardware. So that there's examples of some of those hardwares there. If you looked inside these boxes here, and yours are small now because we did miniaturization, you would see some things like this. So you got a power supply. That's necessary because the power coming into the box here in Qatar is 230 or 220 volts, and it's AC as opposed to DC. You know, AC is alternating current as opposed to DC direct current. So that's an alternating current with that cycles at 60 hertz, 60 times a second. That flips. So that's not the way a computer works. Computer doesn't work on 230 volts and AC cycling. So you have to convert that. And so you've got this device there that's what it does. It takes in the power from the wall. This one's got a fan on it as well, so it's kind of a multi-purpose box. But it takes that power from the wall and it converts it to 5 volts direct current. So the components that are inside there on the motherboard, these devices here, our CPU, our fan, our RAM, they run on 5 volts. And so that's a lot different than 230 volts, right? So you got to have a converter to do that. Yeah, on your laptop, that converter is built into the plug-in, right? And so you'll see that if you pick up the plug and look at it, you'll see, well, actually some of them are 19 volts. So they still have to have another converter inside. Yeah, anyways, so you're going to step down. But these components here, like the motherboard, you see the CPU there sitting in the middle, which is a good place for it, central processing unit. You see all the sort of other parts of that motherboard are arranged around the CPU. And that's because the CPU takes input, processes it, and goes to output, right? And so all of these other components are doing something either with the input or the output. These little slots here, that would be for the memory. So the memory card's going to fit in those slots there. Other slots there would be for other devices that you would add. There would be a graphic card in there or something like that. So yeah, the CPU is going to have a fan on it. That's because the CPUs that we have nowadays, they are so fast and so powerful that they produce a lot of heat. And so heat is not good for electronic components. So that heat has to be removed. And so you have a fan over top of the CPU, and then you have other fans inside the box. The RAM, we've referred to that before. RAM is your random access memory. You can add to it to get to make more powerful computer. So maybe if you're a gamer, you might buy a case like this and a motherboard with a high spec and then add a bunch of components to it, because you could build something that would be much more powerful than your laptop computer for the same price. And then you could have a big screen and all the rest of it. A VGA card, again, if you're a gamer, you would have a card probably that would have a high spec, NVIDIA or something like this. Now you'll notice that this one's also got, on this VGA card, it's got another fan on it. And that's because VGA cards will have their own processor. So because making graphics uses so much computer power, what a lot of computers will do, especially if you're using it for for a lot of graphics, like if you were editing videos or you were running video games, then you don't want the main processor to have to do that. And so you'll put that work off to another processor. And so you have a VGA card that will have a processor on it, and it will just work on the video. So we got some other things there, sound card. These things are often built into the system now. So the sound card, yeah, I mean, if you wanted to have higher quality sound, like you wanted to do, have some kind of Bose system or, hardened card, something like that, you might get a higher quality sound card, but usually you find that that's actually available in the system, on the motherboard itself. Again, with the hard disk. So yeah, you're going to have a hard disk because it's cheaper than SSD. You know what I mean by SSD? A solid state drive. Solid state drive would have no moving parts, and it'd just be transistors. That's nice. The benefit of the solid state drive is a lot faster than a hard drive because it has no moving parts, but it is a lot more expensive. There is some other disadvantage, I suppose, to read all-in-one terminal. So what I don't know, you'll see this with the laptops, like with the Apple laptops, you'll see they're only going to those USB 3 ports, the little ones. So that's sort of becoming a universal port. But yeah, we still have some card readers in some old computers. You might have who's got a camera? Anybody use a digital camera now? Oh my gosh, we thought they were so awesome back in the 2005, 6, 8, 10 digital cameras. And of course they had their own little cards with them. But now this is your camera, right? I mean, they've improved the optics in these smartphones so much that people just use them. And you got all kinds of nice software that goes with them as well. Okay, so I think I talked about the main board, motherboard. Okay, now, so inside the box, okay, we've got all of these elements. These other things we call peripherals because we plug them into various ports and they connect. And you'll notice that the peripherals tend to be input-output devices, or they could be more storage. So if you haven't got enough storage in your case, you might be able to connect and have a external source. Oh yeah, so computers follow instructions. That's true. And this is, now we're talking about software. That previous slide was all about hardware, stuff that you can feel and touch. Software, that's what makes the program work. It is instructions. We've got different kinds of software. We've got software which is the operating system, and we've got software which is our particular applications. How the software works is step-by-step instructions with some gathering of data to go with those instructions. And can you, anybody know some computer software languages? Python, very good. Java, I heard, very good. HTML, okay, I'm going to call that a programming language. It is, because we program web pages. Linux is an operating system, but it's still a programming language. Operating system. I suppose you could write, what could you write? You could write scripts in Linux. You can give Linux instructions, absolutely. So others? C++ is, okay, so C++, Java, and Python, they're all what we call object-oriented languages. So with those languages, you can do, you have objects and you have methods, and it's, yeah, it's a big improvement from the software that was before that, and it works really well on the web. So very good answer so far. There's another question, one over there.
Bash commands.
Bash commands, yes, there we go. So are you using that? All right, good. So there we go. We've got some programming and some commands that we've been talking about. Now, why do we have to mention binary? And that's because the computer only understands binary. The language of the computer is binary. All it understands is zeros and ones. Zeros and ones roughly can be assigned to on, off, or get, yeah, on, off. True, false. True, false works with computers. And so we generally say, well, 0 is false and 1 is true. That kind of sounds okay to me, right? But yeah, so I mentioned the 5-volt thing. So what we can do is we can have between 2 points somewhere in a computer, like on a transistor or a gate on a computer, you can have a current pass across that, in which case it'd be 5 volts. If it doesn't pass across that, then there's 0 volts going across that. So that's our 0 or then our 1. And that's called a bit. If it's a 1 or a 0, it's a bit. Now, a bit, it's, that's a very small unit. What we tend to do is we work in these things called bytes. And what a byte is going to be is 8 bits together, 8 bits together. And so with 8 bits together, we have a number, we have many different states that we can have with 8 bits together. And that is tried to be represented by this thing here. If you have 2 bits, if you had a thing that was just 2 bits, you could have 4 states. I got a pen. Well, look, here they are here. If you had 2 bits, if you got 1 bit, you could have got 2 states, 0 and 1. If you had 2 bits, you could have 0, 0, that's 1 state. You could have 0, 1, that's 2 states. You could have 1, 1, that's 3 states, and you could have 1, 0. Right? So that's 4 different states that you get out of 2 bits side by side. If you had 3 bits side by side, you could have 8 states, right? So they would be, so 3, that's why I wish I had a pen. Well, you know, maybe I could write it if I had a Word document. So let's take 3 bits. You could have 0, 0, 0. Let's make it a bit bigger. That's 1 state. Then you could have 0, 0, 1. You could have 0, 1, 0. Then you could have 0, 1, 1. Then you could have 1, 0, 0. Then you could have 1, 0, 1. Then you could have 1, 1, 1. And how many states is that? If I missed any? 1, 0, 1. 1, 1, 1, 1, 0. Oh yeah, probably should go there. 1, 1, 0 would be here after this. 1, 1, 0. How many states is that? 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 states with 3 bits, right? Did I convince you? There's 8 states with 3 bits, and so on and so forth. So if you had 4 bits together, you could have 2 to the 4 states, because 3 bits is 2 to the 3 states. You all know that 2 to the 3 is 8, right? Because it's 2 times 2 times 2. That's 2 to the 3. 2 times 2 times 2. 3 lots of 2 multiplied by each other. That's 2 to the 3, and that gives you 8. 2 to the 2 is just 2 times 2. 2 to the 4 is 2 times 2 times 2 times 2. 4 2s, right? Multiply it by each other. What's 2 to the 4? 16. 2 to the 5? 32. 2 to the 6? 64. See, you know this, right? These numbers are all familiar, right? They're numbers that people use in computing all the time. So 2 to the 7? 128. And 2 to the 8? 256. Very good. So with 8 bits, we can have 256 states. 256 states is enough to have a bunch of symbols. And so we actually can use that for the English, or not English, yeah, the Roman characters, ABC through Z, plus letters 1, 2, and a bunch of other characters. 256 is enough for that. And I think I might have mentioned the ASCII character set in a previous lecture. I don't know. So how does a computer run a program? What it does is, as it says here, it fetches the next line of code. It takes it one line at a time. And I think we mentioned this in a previous lecture as well. Take it one line at a time, and then it picks that up from the memory, right? So it takes it one line at a time from the memory, then it decodes it in the CPU, and then it executes it. And then whatever the results are, I put in the memory somewhere or output. Okay, so this is nice. We've got 2 different architectures. We talked about Van Neumann before. And so hence Van Neumann's architecture. So Van Neumann's idea being that you have a CPU, and the CPU is connected to 2 different types of memory, and we have data buses between each of them. The difference between that and this other architecture, which is the Harvard architecture, is that the Harvard architecture allows for 2 different buses to coming out from the CPU, each one going to a different one of those memories for the different purposes. So whereas the Van Neumann only had 3 buses there, do you see that there's 6 buses in the Harvard architecture? The Van Neumann architecture is more common. That's what we find in our PCs and stuff like that, although the Harvard architecture is making its way into PCs now. So anyways, what I'm thinking about this, okay, so this is dry theory, right? From a point of view of a student, I suppose. This is dry theory. Oh yeah, why do I care about that? Well, it might be, I don't know, it's going to come up in a test, right? So what would be the question that would come up in the test? It'd be, okay, so what's the difference between a Harvard and a Van Neumann architecture? And then you would know that the Harvard has more buses, and it actually works faster, right? So you can see that the Harvard's got twice as many buses and works faster than the Van Neumann. The other thing is that the Van Neumann's more common in our computers, and Harvard is making its way in. The other thing is that the Harvard is found in embedded devices, and where you have a small device that has to kind of work within another system. The other thing is that because of the way that this data is, you're going to have more memory associated with the Harvard architecture. But that's okay, because memory and processing is getting cheaper, right? And okay, so there we go. How the Van Neumann works. Van Neumann architecture allows for the fetch, decode, execute cycle, and is common in most PCs. So we've talked about that. And then the Harvard, you're going to have 2 different memory units, going to have more buses, and so it's going to be faster, but it requires more memory. It's not found everywhere like the Van Neumann, but it is used in embedded devices. Okay, and there's a fetch, decode, execute, which is the cycle which works with Van Neumann. Now the registers are shown there. That's something that we haven't spoken about. Let's look at each one of these different things here. We've got a control unit and an ALU and a main memory and registers. The control unit and the ALU are both within the CPU. The main memory is going to be outside the CPU, but the registers are inside the CPU now. Register is a form of memory. That's going to be the fastest memory that you got in your computer because it's closest to the CPU. It's actually in the CPU. So control unit and ALU. The control unit is sort of giving the instructions to the, so fetching the instructions is the control unit, and then passing those instructions to the ALU. The ALU actually executes the instruction. So you can see that the control unit does the fetch, the ALU does the execution. So ALU stands for Arithmetic Logic Unit. So hopefully that makes sense, because what it does is it does math, arithmetic, and it does logic. Logic is true, false, if this, then that. All right, so that's the type of logic that we do in computing. We have a lot of if statements and branching, the ALU is going to manage that. The main memory is outside. Now, I mentioned the registers because the register is a short-term, very small place for memory, which is going to be able to handle this, instruction coming over from the control unit to the ALU, etc. I don't know if you know anything about the power, what were they called? Thank you. I've heard of them, but I've never really seen them. But, okay, so if that means anything to you, it doesn't really mean anything to me. But anyways, okay, so culinary analogy, cooking. Fetch would be we go and we get some instructions from the cookbook. Decoding would be to understand the instructions and get the ingredients. The ingredients would be the same as the data, right? And so the data would go to the register and then to the ALU. So in the control unit, this would be happening. In the control unit, we're getting the instructions. Then we pass those instructions to the arithmetic logic unit where they are decoded. And then the data that's necessary for that instruction is coupled with it. And then we execute it and it is done. So I hope that makes some sense. I see people yawning. That means you're kind of tired. So would you like to have a break? Just for a couple minutes. And I'll save this and then we'll come back and we'll do the other one. Does that sound good? 5 minutes, start. Go and so wash your face with water or something like that. Take a break. At least stand up. You don't have to go out.